You know, everything has a breaking point, a limit. But what if we could predict that exact moment of failure before it ever happens? What if we could see the invisible weaknesses that lead to a total collapse and actually stop it in its tracks? So let's really dig into that. It's a fundamental question, one that engineers and scientists grapple with every single day. And the reason they're so obsessed with it is because the answer has massive, real-world consequences. We are talking about the very fabric of the world around us. A tiny, unseen crack can start creeping through a bridge or an airplane wing or a pipeline, growing silently for years under stress until, bang, catastrophic failure. Predicting this invisible threat is, without a doubt, one of the most critical challenges in modern engineering. Now, the main culprit behind so many of these failures is a sneaky little phenomenon called fatigue. And trust me, you already know exactly what this is, even if you don't use the name. You've seen it every time you've bent a paperclip back and forth. Think about it. Every single bend, every vibration, every little cycle of stress adds a tiny bit of damage. It's not one big event. It's a slow, cumulative process. Microscopic cracks form and grow until the material just can't take it anymore. And it suddenly and often very unexpectedly snaps. Okay, so if we know this happens, how on earth have we been trying to predict it? How do we look at a component that already has a small crack and say, you've got another 10,000 cycles left? Well, for a long time, engineers had to rely on what are basically fancy digital handbooks. These things are packed with data from past experiments, and they're fast. But here's the catch. They have to assume cracks are simple, perfect shapes, like a flat oval. But we all know the real world is messy. Real cracks are jagged, complex, and totally unpredictable. And that's where modern simulation comes in. It's trying to model that messy reality. And this is where things get really interesting. This brings us to a breakthrough detailed in some new research. It's a new virtual tool called the Generalized Finite Element Method, or GFEM for short, and it is a much, much smarter way to simulate how things break. Now check this out, because this is where it gets super clever. Think about traditional simulation, like building something with Legos. Every time the crack in your model grows, even a tiny bit, you have to take the whole thing apart and painstakingly rebuild it around the new crack shape. It's a nightmare. But GFEM, it's like having smart Legos. The crack is described by math inside the existing Lego blocks, so the overall structure doesn't need to be constantly rebuilt. This makes the whole thing faster and way, way more flexible. So the secret sauce here is that you can start with a totally normal 3D model of, say, a pipe. You don't even have to model the crack itself. Instead, you just enrich the model with some extra math that tells it, hey, by the way, there's a crack right here, and this is its shape. This is huge because it means the crack can grow and twist in really complex ways without forcing you to do a complete digital rebuild every single time. Of course, a new method sounds great on paper, right? But does it actually work? Well, the researchers decided to put their GFEM tool through the ringer. They didn't just do one test. They validated it against 3 incredibly difficult real-world experiments. For test number 1, they decided to be tricky. They basically set a trap for the crack. They took a steel plate and drilled a hole in it, specifically designed to lure the crack off a straight path and force it to curve and even sink down into the material. And the result? The GFM simulation absolutely nailed it. It was spot on. It predicted that complex, curving path almost perfectly, matching what they saw in the physical experiment. It handled all the weird twisting and pulling forces, and it even showed the crack sinking down exactly where it was supposed to. A massive success right out of the gate. Okay, so it can handle curves. That's cool. But what about one of the most common and dangerous scenarios out there? For the second challenge, they simulated a small crack on the surface of a steel plate and watched as it grew deeper and deeper until it broke all the way through to the other side. Now, you have to understand, that transition from a 2D surface crack to a 1D through crack, that is notoriously difficult to simulate. It's a real headache. But GFEM, it just handled it automatically. The final prediction for how long the component would last was incredibly accurate, lining up perfectly with both the real experiment and other simulations. But they saved the biggest, baddest test for last, the grand finale. For this one, they simulated a crack on the outside of a steel pipe, critical infrastructure, and watched it grow under bending forces, creeping closer and closer to breaching that inner wall. This is a scenario with absolutely enormous real-world stakes. So you're watching the virtual test, and you can literally see the crack front moving, step by step, through thousands of stress cycles. It's creeping its way through the pipe wall, getting dangerously close to that inside surface.
And then it happens. The crock front makes contact with the inner boundary. It's through. The pipe is breached.
And right here, this is the money shot. This is what is so incredible. As the crack breaks through, the simulation shows the single crack front splitting into two separate fronts that then keep on growing. This is a fantastically complex event, a geometric twist that most other simulation tools simply cannot handle. The ability to model this automatically is a massive, massive leap forward.
So, okay, that's some really cool, complex science. But what does all of this actually mean for our daily lives? Well, it's about building a fundamentally safer world.
It means we can predict with much greater accuracy how long a part on an airplane or a section of a pipeline will really last. We can design safer bridges and buildings right from the start without having to make them needlessly bulky and expensive just to be safe. It means we can finally analyze these really complex failure scenarios that used to be a complete black box, giving us the power to prevent disasters before the first tiny crack even forms. Look, at the end of the day, this represents a huge shift in thinking, from being reactive and just fixing things when they break, to being proactive and designing them not to break in the first place. A key part of the research was getting hyper-accurate stress intensity factors. That's basically a measure of the stress at the very tip of the crack. By calculating those with this new level of precision, we can design for true durability. It's like we've been given a new kind of vision, a way to see the invisible forces that threaten to break our world. And it really gets you thinking, doesn't it? If we finally figured out how to accurately predict the breaking point of materials, what other invisible forces are just waiting out there for us to simulate, to understand, and finally, to master?